So this is joint work with my advisor Patrick McDaniel and collaborators from University of Wisconsin and ARL. Here we go. So just to get you started, consider an adversary who's trying to crash a driverless car. The driverless car today uses a camera to identify and locate signs on the side of the road, and then it's going to use a classifier to process this raw image and output the type of the sign. And in this work, we're considering adversaries who are able to manipulate the input of the neural network classifier and who are interested in making it, forcing it to make mistakes. For instance, here you have an image of a stop sign, which is correctly processed by the model. And now, if I consider an adversary capable of introducing this perturbation to the image, the adversary is able to force the model to produce the wrong class. And previous work has shown that this is possible with indistinguishable perturbations and very reliably. So this is not a problem specific to driverless cars. Companies in the industry use neural networks to detect financial fraud, malware, and advanced persistent threats. They also process medical data and genetic data with neural networks. Also, some companies provide deep learning as a service for other developers to include in their products. So before I get started, let me introduce briefly some basics about neural networks so I can lay out the rest of the presentation. So this is an example of a neural network which is solving a classification task, that is that you are trying to map an input domain into a predefined finite set of classes. For instance, here the neural network is trained to recognize digits in images. So the first layer of the neural network is simply reading the image and encoding it as a vector of real values. Then the first hidden layer, is applying a weighted sum to this input layer and then nonlinear functions to produce the first representation of the input. The second hidden layer repeats the same process with different parameters in the weighted sum to produce a second representation of the input, and so on, until you reach the last hidden layer, which has as many neurons as there are classes in the problem, and each neuron produces a score value, which indicates the likeliness of the sample of being in this class. And finally, this is processed by a softmax layer, which is simply taking the class values into probabilities, so normalizing and summing up to 1. And so this whole model is trained by showing it a bunch of input-output pairs and backpropagating error gradients through the model. And it turns out that neural networks have been shown to produce state-of-the-art accuracies in many machine learning tasks in the past 10 years. Another example is this architecture used in the industry to extract meaning from raw audio. And it shows the success of DNN because it is able to replace a chain of tools that require hand feature engineering. And here the neural network is able to extract a hierarchy of increasingly abstract representations automatically. So, however, even though neural networks perform very well on legitimate inputs, previous work has demonstrated that it is extremely easy for adversaries with knowledge of the neural network to find indistinguishable perturbations that will force the model to output a wrong class. So for instance, here on the left, you have our digit data set. On the diagonal, all the samples are correctly classified by the model. And off the diagonal is you will find adversarial samples that are all misclassified by the model. So to read the matrix, the rows are input classes, so they're the legitimate class of the sample that a human being would assign. And the columns are the output of the model. And as you can see, we can craft perturbations that take any sample from any class to any target class chosen by the adversary. For instance, the first row is a 0 classified by the model as a 0, 1, 2, 3 through 9. This works with many data sets. On the right, you will see the CIFAR data set where you can classify dogs as birds, planes as trucks. And below it is a traffic sign data set where you can, for instance, classify a no truck sign into a yield sign. And how this is done is by computing the Jacobian of the model with respect to the current input, which gives you an estimation of the sensitivity of the model. And then you combine these values into adversarial saliency maps, which will indicate for each input feature how likely it is to contribute to your misclassification goal. And you do this iteratively, perturbing the highest saliency features until you are able to force the model to misclassify this sample in a class that you chose. So now I'm going to go to the topic of interest for this talk, which is defending against these attacks. So what are we trying to achieve? So if you consider a simplified picture of the model's output surface, X is a legitimate sample, and the adversary is trying to find the adversarial sample X star that is closest to the legitimate sample, so basically the one that's on the other side of the decision boundary. And what we are trying to do as defenders is push this decision boundary further away from the legitimate sample. We want to do this with a low impact on the architecture so that the solution can be easily deployed in existing systems. We need to maintain accuracy because otherwise the model becomes useless. Related to this, we have to achieve robustness in something that is close to the legitimate expected distribution, or else you could imagine this constant classifier where the decision boundary is to infinity, which would be perfectly robust. And finally, we have to maintain the speed of networks because neural networks are widely used in the industry because they're able to make predictions at test time very quickly, so we don't want to degrade that. So if you remember the model that I showed you earlier, the last layer is the softmax layer, and this is what we leverage to create our defense. The softmax layer works by applying an exponential function to the class scores and dividing by the sum of the exponential values. And there is a parameter in that function, which is the temperature T, which divides the class scores before the exponential function is applied. And what this parameter does is that when you set a low temperature, the probabilities will be extremely discrete, so you will make confident predictions. However, if you increase the temperature, the probability vector will smooth out and converge towards 1 over the number of classes. So typically, people will set the temperature to 1 because they want to make confident predictions. What we saw is we can instead increase the temperature to increase the robustness of the model, and I will show you how. If you have your training data, which is a set of input points and labels that you showed to the network, you can train a first network as you would typically do, to the exception that you raise the temperature to a large value, typically around 40 to 50. And you will produce this way probability vectors that are very smooth. You are going to then use these probability vectors to label your data. That is, you replace the labels that simply indicate the correct class with the probability vectors. You train the same architecture from scratch using this new labeled data set. and you obtain a new model, which we call the distilled model. And to make predictions using this new model, all you have to do is simply set the temperature back to 1 at test time. This way you still have discrete predictions which are confident. And it turns out that this is very efficient in making adversarial sample crafting much harder. So why does it work? What's the intuition behind this? There is actually 2 of them. First is that when models are trained, they typically are trained to minimize a loss function, which is something along the lines of the cross entropy between the expected labels and the predictions. And if you replace a label of the correct class by probabilities, instead of constraining only the correct class to be the output, you allow the network to produce some class scores for classes that are not the correct class. And you can see how this is useful if you look at the 2 images at the bottom of the slide. This 3 here is very similar to an 8. There's only a few pixels that are missing to make it into an 8. And what distillation will do is that it will allow the model to output a class score for 8 here, as long as 3 is larger, as a larger value. And also, it turns out that the Jacobian amplitudes are inversely proportional to the temperature. So as you increase temperature, reduce the Jacobian amplitudes. So we validated this defense on 2 data sets. The digits data set, which previous work has shown you can force to misclassify with a 97% success rate by only modifying 4% of the inputs. And the second data set is a data set of color images with objects and animals. On both of these data sets, we trained state-of-the-art or close to state-of-the-art architectures using convolutional layers, rectified linear units, and the softmax. So here are the results. You can see the blue curve corresponds to the digits data set, and the gray curve to the objects data set. And the x-axis holds the temperature parameter, and the y-axis the success rate of adversaries. And as you can see clearly, as the temperature increases during training, the adversaries have a harder time crafting adversarial samples, and eventually, for the digits data set, we reach levels less than 0.5% success rate, and for the image data set, we go below 6%. So you may wonder, okay, so he's telling us the defense, does it impact the accuracy of the model? Does it impact the performance? And it turns out that the impact on the accuracy is limited. On the left, you can see for increasing temperatures, the accuracy impact is always constrained between a little less than 1.4% and a little over 1.2% increase. So that is, sometimes distillation even increases the accuracy of the model. And this allows you to find sweet spots where, for instance, for the digits data set, for a temperature of 40, we found that we could bring the success rate down to 0.45% while degrading the accuracy by only a little less than 0.5% as well. And the same thing holds for the image with colors of objects. You can set the attack success rate for 6% using a little improvement in the accuracy. So this clearly shows that there's a more general question here, whether you'd like to identify the relationship between accuracy and robustness. And this is an open problem that we are still looking into. So also, the impact of the distillation on Jacobian amplitudes. As if you remember earlier, I said that the Jacobian amplitudes are inversely proportional to temperature. And you can see that we measured this empirically each histogram is for a given temperature. The one on the left is no distillation, and the one on the right is the highest temperature. You can see that initially the Jacobian amplitudes are between 10 to the minus of 3 and 0. And as you gradually increase the temperature, you decrease the Jacobian amplitudes up to, well, actually down to 10 to the minus 40. So there is a reduction by a factor of 10 to the power 30 of the Jacobian amplitude, which effectively smooths the model's decision boundaries. And we estimated the robustness because it is not possible to compute it exactly. So what we did empirically is we considered the test set for each data set, and we computed all possible adversarial targets for each input, and we identify the smallest perturbation which achieves misclassification in any class that's different from the legitimate class. And it turns out that this gives us a way to compute the average minimum perturbation to achieve misclassification, which is the definition of robustness. And you can see that for the digits in blue and the objects in yellow, we indeed have a reduction, an increase in the average minimum perturbation. So to conclude, distillation significantly reduces attack success and yields model smoothness because of the Jacobian being smaller. We have an easy implementation. All you have to do is loop twice through training, and an acceptable impact on accuracy, even sometimes improving it. If you have any questions, I'll be happy to answer them. Thank you.
Hi, I'm Pavel Laskov from Huawei Research in Munich. Thanks for a very interesting talk on such an unusual subject. Does your method somehow consider the constraints on the attacker? Let's say, is the attacker constrained in obtaining adversarial samples in a certain number of iterations?
So are you asking basically about the assumptions that we make on the adversarial knowledge?
Right. So what sounds a little counterintuitive to me is that your method essentially is trying to increase the smoothness of the Jacobian, and intuitively, with very unstable Jacobian, attacker can very quickly attain his goal.
Yes.
So if the Jacobian becomes smoother, then the relative effect of the attack would become smaller.
Yes.
But an attacker might, well, say, willing to wait for a long time, might still achieve his goal. So have you considered this sort of temporal factor in the behavior of the attack?
So this attack here, when you craft an adversarial sample, you do not impact the training set. So the impact of an adversarial sample is instant. It's instantly misclassified. What we showed here is that it takes more perturbation to produce adversarial samples with distillation. We didn't say that we completely solved adversarial sample, the problem of them. All that we have is that the adversaries need to use much more perturbation to achieve their goal.
Okay, and are they constrained on the amount of perturbation they're allowed to have? Let's say.
Well, it depends on the application data. For instance, here for the digits data set, if you start increasing too much the perturbation you introduce, then even as a human, you will misclassify them because there's so much noise in the image. So that's why the adversary is interested in minimizing the perturbation.
Okay, well, thanks.
Thank you.
Okay, go ahead.
Do you have any backup slides where you can show us what the minimum perturbed ones look like with your system? What the ones that look like nines look like?
I do not have that.
Do humans look at them and say, oh, that's a 9 instead of it's a 1?
We haven't studied that with distillation. In previous work, we studied the perception of humans on adversarial samples, what we saw was that they would misclassify them above a certain threshold of perturbation. And the defense here is basically bringing the minimum average perturbation to that threshold. So I assumed that if you were to repeat the same study on human perception, you would find that humans would find these samples as non-acceptable as well.
Thanks.
Thank you.
I just have a question for the adversary model. So do you give the neural network description also to the adversary? Or?
I'm sorry?
So what is the exact knowledge of the adversary? Do you give him the description of the neural network also?
So the attack that we use to evaluate the defense assumes that the adversary has access to the model parameters and the architecture. However, in more recent work, we showed that this knowledge is not required to conduct the attack. And as a matter of fact, adversaries can conduct black box attacks on any machine learning technique by training substitute models for their target.
So I'm going to ask a very quick question and then we'll move on.
Yes.
So the applications that you focused on were computer vision tasks. And I'm wondering how this would work with other sorts of classification, like suppose just looking at the sensors on your smartwatch or your smartphone and doing activity recognition. Or
so I haven't made that public yet, but I have studied attacks on malware classifiers, and the attack is still possible. If the neural network is trying to detect malware, you can invade it this way. I haven't studied the impact of the defense yet.